In this lecture, I am going to explain how to design CMOS circuits using complementary static CMOS design style. A complementary static CMOS circuit consists of two networks. One is pull-down network, other one pull-up network. This is pull-up network and this is pull-down network. This figure is a generic N-input logic circuit. Now, let us see what is the function of pull-up network. Pull-up network is to provide connection between the output and ground. This is the output, this is the output, and this is VDD. So pull-up network function is to connect circuit from VDD to ground. Similarly, let us see the function of pull-down network is to connect the output to VCC. Now this is output, it connects to VCC. So pull-up network connects VDD to output and pull-down network connects output to ground. These are the functions of pull-up and pull-down network. When pull-up network connects VDD to output, when the output logic is 1, and when pull-down network connects output to VSS, when the output is meant to be 0, right? Now pull-up network and pull-down networks, they are constituted in a mutually exclusive fashion. That means only one network conducts at one time. Okay, so that means pull-up network consists of all P transistors, pull-down network consists of all N transistors. And now, in this way, we can say when once the transients have settled, a path always exists between VDD and the output F, realizing a high output 1, or alternatively between VSS and F for low output. Okay, so I think you are able to understand what is the function of pull-up network and pull-down network. So when the output is 1, VDD is connected to F. When output equal to 0, output is connected to VSS ground. Therefore, it will be 0. Now let us see some points we have to keep in mind while designing this pull down and pull up networks in constructing these pull down and pull up networks. One thing is a transistor can be thought of as a switch controlled by its gate signal. That means the MOS transistor has gate, source and drain, and depending on the voltage that we apply at gate terminal, the transistor will be in on condition or in off condition. For example, an NMOS switch is in on condition when the controlling signal is high and is in off condition when controlling signal is 1. That means what? N switch or NMOS transistor is on when we apply 5 volts and it is in off condition when we apply 0 volts. Otherwise, N is on when we apply logic 1 at the input and it is 0, it is off when we apply logic 0 at the input. Similarly, PMOS transistor acts as inverse switch, that is, it is on when input is low and off when control signal or input signal is high. Just reverse to N transistor. So hope you followed what is N switch and what is P switch. N transistor as a switch, when the input is high, N transistor will be in on condition, on switch, and when input is low, N transistor will be in off condition. Vice versa with P transistor. Now second point that we have to keep in mind is the pull down network is constructed using NMOS devices only, while PMOS transistors are used in pull up network. Already I have mentioned pull up network is designed with P transistors, pull down network is designed with N transistors. Why? What is the reason? Means you can say NMOS transistor produces strong zeros and P transistor generates strong ones. Right? Now let us see some set of rules to construct these circuits, these logic functions. NMOS devices connected in series like this, okay, acts as an AND gate. That means when the inputs, both inputs are high, at gate applied A input we have applied logic 1 and B also logic 1. Therefore, this is on switch and this is also on switch. Therefore, input passes freely to the output. Therefore, it is an AND gate. If both A and B are 1, output is 1. Otherwise, output will be 0. So, like that, we can say N transistors, when they are connected in parallel, it represents R function. So, this is N transistor and another transistor, they are connected in parallel, it constitutes an OR function. That means output will be equal to A plus B, and here output will be equal to A dot B. So these are the things we have to keep in mind. Now let us say a 2-input NAND gate. So 2-input NAND gate in complementary static CMOS design style. So this is pull down network and this is pull up network. In pull down network, we have N transistors and AND function, and this is F. So A dot B bar, right? These are all complementary. Therefore, we have bar at the output. And because N transistors are connected in series, P transistors are connected in parallel in pull-up network. So this is a 2-input NAND gate. Now let us see its functionality. When both inputs are 0, 0, right? This is 0, this is 0. Therefore, this A transistor is in off condition, B transistor is also in off condition. When both are in off condition, and here if you observe, for logic 0, P transistor will be in on condition, P transistor is in on condition. Therefore, this VDD reaches this point F and capacitor connected at the output will be charged to VDD and we will have output equal to 1. So, this 1 can be seen here. So, when inputs A and B are 0, 0, output is 1. And when we say 0 and 1, A is 0 and B is 1. When this is 0, it is off switch. Therefore, there is open circuit from here to here. And when A is 0, this transistor will be in on condition, and of course B transistor will be in off switch. So therefore what happens? VDD is passing through this and it reaches F, and therefore output will be equal to 1. Like that, for all input combinations you can verify the functionality of NAND gate. This is a 2-input NAND gate in complementary static CMOS design style. Now, similarly, we can construct NOR gate. So, for OR function, we have to connect N transistors in parallel. Therefore, when N transistors are connected in parallel in pull-down network, they are connected in series in pull-up network. And where pull-up and pull-down networks meet, we take output F. So, this is F equal to A plus B bar, that is NOR gate. So similarly, we can construct different logic circuits like with n number of inputs. Now another example is 4-input NAND gate in complementary static CMOS style. So because it is a NAND gate, all transistors should be connected in series in pull-down network. Therefore, A, B, C, and D transistors are connected in series in pull-down network, and therefore P transistors are connected in parallel in pull-up network. So where these two join, we take output F. So like that, we can design any circuit using complementary static CMOS design style. Okay, now let us take a Boolean function, right? Some Boolean function which is a complex function, and try to implement with the knowledge that we have gained. Let us try to implement this Boolean function with the complementary static CMOS design style. So here if we take this function, we have output are F equal to D plus A dot B plus C whole bar. Because these are complementary circuits, bar will be there, and B plus C means transistor with the B input and the C input, they should be connected in parallel because to have OR operation, and that parallel combination should be in series with A transistor, and this entire combination should be in parallel with D to design a pull down network. Let me show you this pull down network. First we derive pull down network, later we derive pull up network. Now let us see, this is the equation B plus C. Therefore, B and C are connected in parallel, and it is A dot B plus C. Therefore, this parallel combination is in series with A because we have to get this product, and this is in plus D plus something. So, therefore, this entire combination is in parallel with D. So, like this, we design pull down network, and just complementary to this, we design a pull up network. That means you can see B plus C, B and C are in parallel in pull down network. Therefore, in pull up network, they should be in series. So, B and C are in series. Now, this parallel combination is in series with A in pull down network. Therefore, it should be in parallel with this in pull up network. So, BC series combination is in parallel with A transistor, right? Now, this entire thing is in parallel with D, and here this entire combination is in series with D. So, like that, pull down network and pull up network are designed, and these two are joined or combined to form a complete circuit. So, let us see that. So, complex CMOS gate, this is pull down network BC. B and C transistors are connected in parallel, and it is in series with A, and the total combination is in parallel with D. So, this is pull down network, and complementary to that is pull up network. In this manner, we can implement any Boolean function by using this complementary static CMOS design style. Hope you followed, and now let us see some of the features of this. That means the complementary gate is naturally an inverting circuit. Therefore, it is suitable for functions such as NAND, NOR, and XNOR gates. If you want to realize non-inverting Boolean functions, then like AND gate, OR gate, XOR gate, like that, non-inverting Boolean functions, then this single stage is not sufficient. We have to add extra inverter stage. For example, we have NAND gate F equal to AB bar. And now in order to eliminate that bar, what we have to do? We connect one more inverter. So F equal to AB bar, and that output is connected to inverter. Therefore AB bar is eliminated. We will get A, which is AND function. Like that, inverting functions and non-inverting Boolean functions can be implemented by using this complementary static CMOS design style. Now here another property that we have to mention is number of transistors required to implement n input logic gate is 2 times n. We have seen for a 4 input gate, 4 pull down transistors and 4 pull up transistors, 8 transistors are required. So like that, if n increases, number of transistors required will be increasing. That is the property of this complementary static CMOS design style. Now, with the knowledge that we have gained, I hope you will be able to implement these given Boolean functions. B plus C and B and C transistors are connected in parallel. That combination will be in series with the D transistor, and entire combination will be in parallel with A transistor. Similarly, if I give another function like B plus A, transistor B and A will be in parallel with each other, and total combination will be in series with D, and entire combination will be in parallel with C. Hope you have enjoyed this lecture, and if you have any doubts, you please mention them in the comment section below, and if whether you are able to implement these given two Boolean functions in complementary static CMOS logic style or not, you please mention in comment section. Thank you.